Hello everyone. Today, I'm delighted to present a paper published by our project team in IEEE Transactions on Communications titled Environment-Aware Codebook Design for RIS-Assisted MU-MISO Communications, Implementation and Performance Analysis. I will divide the presentation into 6 parts: background, system model, channel chaining-based protocol, theoretical performance analysis, simulation results, and conclusions. First, we know that obtaining the accurate channel state information and optimizing the reflecting coefficients at the RIS constitute two major challenges in RIS-assisted wireless communication systems. Specifically, the optimization of RIS reflecting coefficients critically relies on the accurate channel state information. We know that instantaneous CSI is challenging to obtain, while statistical CSI is easier to obtain and possesses a longer channel coherence time. The existing statistical CSI-based scheme performs a good adaptability to channel environments. However, it suffers from performance penalty for the scenery with rich scatterers compared to the optimum RIS configuration performance. Moreover, it exhibits poor scalability. Furthermore, we can enhance the performance of the RIS-assisted communication system through the utilization of codebooks, which can strike a flexible trade-off between system performance and training overhead, and has a low complexity in passive beamforming. However, existing codebook schemes such as random codebooks and uniform codebooks usually entail significant training overhead and lack adaptability to channel environments. Moreover, it is important to know that the effects of channel estimation errors in channel chaining-based protocol has not been evaluated in previous research. Therefore, designing an environment-aware codebook scheme based on statistical CSI may enhance the adaptability to channel environments and strike a flexible trade-off between system performance and payload overheads. Against this background, in this paper, we investigate the environment-aware codebook design in RIS-assisted multi-user MISO communication systems. As shown in Figure 1, we have a RIS-assisted multi-user communication system. The number of the BS antennas is set to M. The number of the reflecting elements at the RIS is set to N. The number of the single antenna users is K. Then, the composite end-to-end channel from the BS to user K is given by the sum of cascaded channels and the direct channel, where these three channels represent the baseband equivalent channel from RIS to user K, from BS to RIS, and from BS to user K respectively. Phi denotes the reflection coefficients matrix of the RIS. Therefore, during the uplink channel estimation stage, we can obtain the pilot signal received at the BS, where PUL is the average power of the pilot simples, XK is the pilot simple transmitted from user K to BS, and Z is the additive white Gaussian noise at the BS. During the downlink stage, we have the downlink complex baseband signal received at user K, where omega k is the transmit beamforming vector of user I. Si is the transmitted information symbol of user I, and Nk is the additive white Gaussian noise at the k's user's receiver. Besides, we adopt a quasi-static flat fading channel model for all links, i.e., the channel parameters within a channel coherent block are time invariant. We introduce the baseband equivalent channel and take the channel from the RIS to the user K as an example, where beta R is the path loss of the channel, Fr is the ration factor of the channel, HRK loss and HRK unloss represent the loss and unloss component of the channel respectively. To design the environment-aware codebook and decide the optimum codeword used for assisting in downlink data transmission, in this paper, we propose a channel chaining-based protocol by dividing the codebook generation and codeword configuration into two stages. As shown in Figure 2, it is the frame structure of the proposed protocol. Specifically, during the offline environment-aware codebook design stage, we first generate virtual channels based on statistical CSI, which includes the path loss, the loss component, and the distribution of the unloss component of the practical channels. Therefore, we can obtain the virtual RIS user K channel at the Q's training block, where HRK loss is the loss component of the virtual channel and it remains unchanged within each channel coherence block. HRKQ unloss is the unloss component of the Q's virtual channel, and it is randomly generated following the same distribution with the practical channel. Furthermore, the virtual BS RIS and the BS user K channels are generated in the same way. After generating these virtual channels, we perform alternating optimization to obtain the environment-aware codebook. Specifically, we have the sum rate optimization problem of the MU-MISO communication system. Here is the sum rate of multiple users, and we notice that the constraint includes the RIS-RCS and total transmit power. We adopt the zero forcing beamforming to achieve inter-user interference elimination, and the PQ donates the received power matrix. In the alternating optimization algorithm, we adopt the sensory refinement method to optimism RCS as the RIS and the classical water filling power allocation algorithm to perform transmit power allocation. Repeat for Q chaining blocks. We obtain the environment-aware codebook. It is important to know that all the aforementioned operations are conducted offline. Next, during the online RIS configuration stage, we perform composite channel estimation, where we adopt a mutual orthogonal pilot design and consider the minimum pilot overhead T equal to K, and thus the least squares estimate of the composite channel of the Q's training block can be obtained. Then we adopt the ZF per coder, and thus we can obtain Q sum rate corresponding to Q codewords generated offline. We selected the optimum codeword corresponding to the maximum sum rate and adopt it into downlink data transmission. Then we theoretically analyze the performance of the proposed environment-aware codebook in perfect and imperfect CSI scenarios. First, we introduce the effect of the channel estimation errors on the proposed environment-aware codebook scheme in Figure 5. It can be seen that the channel estimation errors distort the composite end-to-end channels, which is shown by the green arrow. This results in that the optimum index with channel estimation errors may not be correctly selected. Then, consider the errors on the conventional channel estimation and passive beamforming schemes shown in Figure 6. We can see that the effect of channel estimation errors is reflected separately at each phase shift. Note that the influence of the channel estimation errors is implicitly reflected in the selection of the index, whose effects are difficult to accurately characterize. We derived a tighter upper bound of the received power, specifically for n much greater than 1. we have the average signal power received at the user in imperfect CSI scenery, where f1, f2 are related to radiation factor and c is a constant. When the channel estimation errors are adequately small, the theoretical received power in the perfect CSI scenery can be obtained. And here are 4 special cases corresponding to different sceneries. Specifically, if FR approaches 0, it degenerates to random codebook scheme. If it approaches positive infinity, proposed scheme can achieve the optimum system performance. If the training overhead is set to 1, proposed scheme reduces to statistical CSI-based scheme, and if it is set to the maximum value, we arrive at the quadratic scaling law of the average received power with respect to n. To validate our hypothesis, we conducted corresponding simulations. Here are some settings of our simulation parameters. As shown in Figure 7a, we compare the achievable rate with the training overhead in imperfect CSI scenery, and the result of the imperfect CSI scenery is shown in Figure 7b. It can be seen that the proposed scheme can gradually improve the achievable rate with the increase of the training overhead. Moreover, in both the scenery of perfect CSI and imperfect CSI, the derived theoretical performance bound serves a tight upper bound of the simulation results. Compared to Figure 7a, Figure 7b shows moderate performance degradation in the proposed scheme when confronting with diverse channel conditions, indicating stronger robustness against noise. Figure 8 evaluates the sum rate versus the total transmit power. We can observe a logarithmic increased relationship between the sum rate and the transmit power at the BS, which corresponds to our theoretical formula. Then, as shown in Figure 9, we compare the sum rate with the number of RIS elements. It can be seen that with the increase of the RIS element n, the sum rate of the proposed scheme increases with diminishing return, which is due to the fact that a larger number of reflecting elements could reap more radiating energy by coherently superimposing all the cascaded links. Next, Figure 10 examines the effect of the overhead on the performance of the proposed scheme. It is noticed that as the training overhead Q increases, the proposed scheme gets a certain promotion in terms of the sum rate and always outperforms the random codebook scheme as it utilizes statistical CSI to design the RCS. Finally, Figure 11 examines the effective sum rate versus the channel coherence time. We can observe in Figure 11 that the proposed scheme can flexibly adjust the training overhead according to the specific channel coherence time to achieve the highest effective sum rates. To sum up, in this paper, we proposed an environment-aware codebook design based on statistical CSI for RIS-assisted multi-user MISO communication systems. We consider the influence of the channel estimation errors on proposed codebook-based scheme. We derived the theoretical received power scaling law of the proposed scheme, both in perfect and imperfect CSI scenarios, and it is shown that the proposed scheme can strike a flexible trade-off between performance and training overhead according to the specific channel coherence time. The following are some references of this paper. Thank you again for listening. Goodbye.